Hi, today we're going to be talking about the step response of an RLC circuit. Until now we've seen two configurations of RLC circuits, the RLC circuit in series or in parallel. Strictly speaking, it doesn't matter how we calculate our RLC circuit. All of these circuits that we've seen until now are second-order linear time invariant systems. And as such, they all behave in a very similar way. So the transfer function, the denominator of the transfer function, which is also called the characteristic equation of any second-order linear time invariant system, looks like this. Again, s squared plus 2 alpha s plus omega 0 squared. Omega 0 is in many cases called the natural frequency, in many other cases the resonance frequency, and alpha is called the Neper frequency. So depending on how our transfer function looks like, we will have a different value for alpha and a different value for omega 0, but they will all have that. And there is also so basically, when we're interested in calculating the poles of our transfer function, we have to set this equation to 0 and solve for s. And we can do that, and we would get that s. We get two different solutions because we have a quadratic equation here. Would be minus alpha plus minus square root of alpha squared minus omega 0 squared. These would be the roots. It doesn't matter how the circuit looks like. If it's second-order linear time invariant, it has these poles like this. Now, an important parameter that we should also take into account when we're looking at second-order systems is called the damping factor, which is represented by the Greek letter zeta, which I can't draw very well, but you can imagine that it's a nice one. And it's basically defined as alpha over omega squared, omega 0. Sorry, alpha over omega 0. So, now, there are very complicated equations that describe the time domain step response of such system. You can find them in the script. I will not write them down here. The important thing to know is that the particular response of your circuit will depend on these parameters and specifically on the damping factor. So it depends on alpha and on omega 0, which in turn depend on the choice of components that you have in your circuit. So we have several possible responses. And here we can see many curves, yeah? Each of the curves is one response for one particular value of our damping factor. So if we have, we can see here, my damping factor can be 1, or can be more than 1, or it can be less than 1. So if it's exactly 1, we say that our response is critically damped, and it corresponds exactly to the blue thick curve that's written here. So that is the critically damped case, and that is when our damping factor is exactly equal to 1. Now, when our damping factor is less than 1, it means that it's underdamped. Just making sure that I have the right. Yes. So when zeta is less than 1, it means that my system is underdamped. So I will have all the curves that are above this one, all the curves that oscillate like this are underdamped. So the higher the curve and the higher the oscillation amplitude, the lower our damping factor is. So it's less damped, so it oscillates like this. And all the curves that are below our blue curve are when zeta, or damping factor, is more than 1, and we say that then that the system is overdamped. So it kind of takes longer to reach the final state as well. So depending on the particular circuit that we have, we might have a response that doesn't look exactly like this. For instance, if we measure the output of our RLC circuit that's in parallel, let's say I have a step on the input, and so basically both my capacitor and my inductor will charge with time. And we know that when the capacitor is completely charged, it will behave as an open circuit, and when the inductor is completely charged, it will behave as a short circuit, right? And if I measure my output voltage here, then my output voltage when the circuit is completely charged will be 0, because I cannot have any voltage drop across a cable. So this curve will basically oscillate around the value of 0 if I measure my output here. If I measure on an RLC circuit in series with the output at C, then my circuit would look like this, RLC, and I measure my output voltage here. When the inductor is fully charged, it's a cable like this. When my capacitor is fully charged, it's an open circuit. So there is no voltage drop across here because the current is 0, my circuit is open. So the voltage I measure here is the input voltage. So if my step has the size of 1, my output will look exactly like this, depending on the values of R and L and C, which set again my values of alpha and omega 0 and my damping factor. So that will look exactly like this, because the end voltage that my circuit can possibly have when all the components are fully charged has to be the input voltage. If my input voltage is 1, it will look exactly like this. But in general, we can say that my step response, it doesn't matter what RLC circuit I have, will look like this. And it will depend on the choice of components of our values. Now, something very interesting that I need to mention right now. Let's look at when we calculated the transfer function of our parallel circuit, we ended up with a characteristic equation here. So my characteristic equation is for the parallel circuit, I'm going to write parallel. When R1 equals R2, my characteristic equation looks like this: S squared plus S times 2 over RC plus 1 over LC. Whereas my series circuit, it doesn't matter if it's where we measure the output. For all series circuits, my characteristic equation is the same for all of them, and it's S squared plus R over L times S plus 1 over LC. So in this case, I have alpha is 1 over RC, right? Because I had 2 alpha on my equation before. Wait a second. Yeah. And in this case, my alpha is R over 2L. R over 2L. So basically, the omega, look at this, omega squared is the same for both circuits. So it doesn't matter if it's series or parallel, they all have the same resonant frequency or natural frequency. Basically, we said that our theta is equal to alpha over omega squared. Sorry, omega 0, alpha over omega. Yeah, and omega is the same for both, but alpha is not. And what's interesting is that in the case of the parallel circuit, my damping factor is inversely proportional to the size of my resistance. Whereas in the case of my series circuit, the damping factor is directly proportional to the value of my resistance. So for a series circuit, for a parallel circuit, if I need to increase the damping factor, namely draw the curve further down, if I need to increase it on a parallel circuit, I need to reduce the resistance. If I want to decrease it in a parallel circuit, I have to increase the resistance. And in the series circuit, is the other way around. So in the series circuit, since the damping factor is proportional to the size of the resistor, if I need to increase the damping factor, namely bring the curve down, I need to increase the resistance. If I want to reduce the damping factor in a series circuit, I need to reduce the value of the resistance. It's counterintuitive when we look at parallel circuits, because we usually tend to think that the resistance is always directly proportional to the damping factor, but it's not always the case. It depends on the case, on the particular way the circuit looks like. So, yeah. This is pretty much it about the step response of the RLC circuits, and on the next videos we will talk about the frequency response. Thanks for watching.